Okay, we have here today a really interesting looking integral on the board. We have the integral of ln of 1/2 to ln of 2 cos x over 1 plus 5 tan x dx. Okay, I've got a whole bunch of concerns here and a few things to be worried about. The bounds are kind of unusual, having natural log in here. The other thing that we don't see very often is we have cosh. We've got the hyperbolic trig function with the regular trig function. But one thing I want to notice right away, ln of 1/2, this is actually the same thing as minus ln2. So we actually have our bounds symmetric around 0, which makes me think that we could possibly use a substitution like u equal to minus x. And of course, then that means x is going to be minus u and dx is going to be minus du. Because what that's going to do is that's going to flip our bounds around and maybe we can use that. So let's just go ahead and make this substitution. So when I plug ln2 in for x here, we have minus ln2. And then when I do the same thing here, I think I'll use the minus ln2. When I plug that in here, we're just going to have ln2. And then we're going to end up with cosh of minus u here in the numerator, 1 plus 5, doing this kind of careful, tan of minus u, and then we're going to have a minus du. Well, the first thing I can do is take this minus sign and use to swap the bounds. So I'm going to just flip this back, putting the minus sign here. And what that's going to do is that actually puts the bounds back to where they were here. Now let's look at cosh of minus u, and what I want to do to be careful is let's just recall what cosh is. Cosh is going to be e to the x, but I'm going to plug in minus u here. That's going to be plus e to the minus x, but again, plugging in minus u, and this is going to all be over 2. Well, here the minus is going to cancel with minus. Okay, so then just cleaning it up, we're going to have e to the u plus e to the minus u over 2. But this is actually the definition of cosh, so this is actually the same thing as cosh of u. So what I'm going to do is just get rid of this minus sign right here and leave this as cosh of u. Now we could have done this quicker just by noticing it's an even function. If we recall that cosh is an even function, we could just get rid of our minus without doing this step right here. Then here for tangent, I'll tell you that tangent is an odd function because sine is in the numerator and sine's an odd function, so we're just going to bring the minus sign out there. But now noticing the pattern where we've got our bounds back to where they were here. We got our numerator back to where it was here, except with a different variable. Well, what if I can change my denominator to get this denominator to look like that? All I need to do for that is if I multiply this, we'll multiply numerator and denominator by 5 times tan of u. I think this is going to work out when I multiply this in. When I distribute 5 tan u times 5 minus tan u, the exponent becomes 0. We end up with 5 to the 0. I'm just going to write that as 1. I'm going to change the order, and then I'm going to write, and then if I multiply 5 tan u times 1, we're just going to get our 5 tan u back. So this is exactly like our denominator. And then for the numerator, I'm just going to multiply 5 tan u times cosh u. Now that we have everything lining up with our original integral, I'm going to change my variable name. I'm going to change my variable back to x. Then at this point, what I'm going to do is we'll just label the original integral I, and then I've just manipulated it to this version of the integral I, and we'll just add these two together, and let's see what we have. Okay, now adding these together, just notice I'm going with this, I'm just going to use this minus ln2 for our lower bound and not really worried about ln and a half anymore, just noticing they're the same thing. And then now at this point, what we can do is, I just noticed if I factor out a cosh x, we have some canceling going on. So let's see, if I just factor this, we'll factor out a cosh x. And when I do that, that's just going to give me 1 plus 5 tan x here in the numerator. But that's really nice because then what I do is cancel here, and then we're just integrating cosh x. But a couple of good things about cosh x. By doing what we did earlier by changing the sign on the cosh, we noticed that cosh was an even function. Well, if cosh was an even function and we have symmetric bounds, we have this property where I can change the lower bound to 0. If I can use my pen, and we can bring a 2 out front. But that's going to help me out a little bit because I have this 2 in front of the I, 2 here. If I divide by 2 on both sides, now we just isolated I, so we're solving for our integral. But the other good news is cosh x is a really easy integral. The integral of cosh x is going to be just sinh of x. So all I need to do is just evaluate sinh x from 0 to ln of 2. But when I do this, I think to make it easier, I'm just going to write out the definition of sinh x. So sinh x is going to be the same thing as e to the x minus e to the minus x over 2. And now we're just going to plug in values. So first plugging in ln2, we're going to have, this is going to be e ln2 minus e minus ln2. But we found earlier minus ln2 is the same as ln 1/2. So I'm going to go back to that notation just for convenience. Then here we got our 2 here. Minus, then we need to plug in 0. This is going to give me e to the 0 minus e to the 0 over 2. Well, e to the 0 is 1, e to the 0 is 1, 1 minus 1. This whole piece is going to 0. So I'm just gonna clean up the board and we'll calculate this last piece and finish it off. Okay, now just continuing where we left off, we just have this expression to calculate. Now this isn't gonna be too hard. So e to the ln 2, that's actually just gonna be 2 because it's like the e and the ln cancel. And then the same thing here, this is gonna give me a minus 1/2 all over 2. 2 minus 1/2 is 3/2, but we're dividing by 2. So for my final solution, we're just gonna have 3 over 4. Okay, really fun problem. We'll stop it there. Thanks so much for watching. Have a great day.